Hi, I'm Maurice Dupre, and in this section we're going to discuss the fundamental theorem of calculus. The two main problems of calculus are to be able to find the tangent line to an arbitrary curve and to be able to find the area inside an arbitrary curve. The fundamental theorem of calculus actually relates these two things very closely. Let's see how it works. We'll begin with a theorem we call the mean value theorem for definite integrals. The mean value theorem for definite integrals. If f is continuous on the closed interval a comma b, then at some point c in the closed interval a comma b, we have f of c equals 1 over b minus a multiplied by the definite integral from a to b of f of x dx. The reason we call this the mean value is that we think of this quantity as somehow representing the sort of overall average value of the function. Notice, if you average two numbers, you add them up and divide by 2. To average three numbers, you add them up and divide by 3. Here, the function f of x is sort of giving us a whole infinite family of numbers as the x itself ranges over the interval from a to b. So it's that length from a to b that we divide by for the averaging process, and so consequently we define the average value to be 1 over b minus a times the integral from a to b of f of x dx. This integral is sort of like adding up all the values of the function over that interval. Now, to see why it's actually true is pretty easy. Because the function is continuous on the closed interval ab, it has a minimum value and a maximum value. So if I look at the horizontal line whose height is the minimum value, notice it's making a rectangle which fits under the curve. Here, for simplicity, we'll take the example where the curve is above the x-axis. Then if I look at the rectangle whose height is the maximum value, notice the area under the curve fits entirely inside the big rectangle. So consequently, the area under the curve certainly has to be between the two areas. The area of the small rectangle is little m times b minus a. The area of the big rectangle is capital M times b minus a. And so consequently, the area under the curve, which is represented by the definite integral of f of x from a to b, has to be between those two values. So if I divide through in this inequality by b minus a, notice that I'll get a number which is between the minimum value and the maximum value. In other words, when I look at this average value, what we call the mean value of the function, it is definitely some number between the minimum of f on ab and the maximum of f on ab, and therefore by the intermediate value property for continuous functions, it must be a value of the function at some point c in ab. Now, the fundamental theorem of calculus is a consequence of this mean value theorem, and the fundamental theorem of calculus says if f is continuous on the closed interval ab, then the derivative with respect to x of the definite integral from a to x, f of t dt, equals f of x on a comma b. That is, if I look at the definite integral from a to x as a function of x, this upper limit, the lower limit's fixed at a, the upper limit is now variable, so now I have a new function of x. The derivative of that function at x is simply f of x. And moreover, if capital F is any antiderivative of little f on the closed interval a comma b, then the definite integral from a to b of f of x dx is capital F of b minus capital F of a. Notice this first part of the fundamental theorem of calculus is telling us that this function, definite integral from a to x of f of t dt, as a function of x is a particular antiderivative of the function f. See, we differentiate it and we get f of x. So what do we know about two functions which have the same derivative? If capital F is any antiderivative of little f, then it is really the same as this function up to a constant. That is, the difference between capital F and this one can only be a constant. And so consequently, when I take the difference in values of capital F between the limit endpoints a and b, whatever constant would have been needed would cancel out. For instance, if capital F plus 10 is what's required to give this area function, then f plus 10 at b minus f plus 10 at a, the 10s cancel, and we end up with f of b minus f of a. In other words, you can see that that expression will not change no matter what constant is added to the capital F. Well, let's see why it is that this is true. Let's look at the picture. Here, in this picture, I have a function y equals f of t to distinguish between the x and the t, and the area under the curve from the limits a to x is denoted capital F of x. In effect, this is then the definite integral from a to x of f of t dt. So our question is, how can we differentiate it? Well, to differentiate it, what we want to do is look at the difference between f of x plus h and f of x, and then once we've done that, let's begin by computing that difference. So in terms of the integrals then, we want to compute the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. Well, notice that's just the definite integral from x to x plus h of f of t dt. Well, let's look at this picture here. From here, a, over to x, this shaded portion under the curve is the area which represents the integral from a to x of f of t dt. And now, the integral from a to x plus h of f of t dt would be the area under the curve from x equal a all the way over to x plus h. And so consequently, when I take the difference, all I'm getting is the definite integral from x to x plus h of f of t dt. That's, in this picture, the area under the curve. Notice the rectangle here at the minimum value for the function during the interval x to x plus h is entirely smaller than the definite integral from x to x plus h of f of t dt, whereas if I take the rectangle with the maximum value, it's bigger. And consequently, by the mean value theorem for integrals, definite integrals, we know that at some point, which I'll call c sub h, between x and x plus h, I can get just the right height so that the rectangle having this area, h times the height, will be equal to the definite integral. That is, the definite integral from x to x plus h of f of t dt equals h times f at c sub h. Or an alternate way of saying that, directly as a consequence of the mean value theorem for definite integrals, 1 over h times the integral from x to x plus h of f of t dt equals f at c sub h for some point c sub h between x and x plus h. So now notice this is the difference quotient for our definite integral with upper limit the variable x. In other words, when I look at the definite integral from a to x of f of t dt and form the difference quotient, value at x plus h minus value at x divided by h, this is the expression I get, and by the mean value theorem for definite integrals, it's f at c sub h for c sub h some point between x and x plus h. So now what happens as h goes to 0, The c sub h is squeezed between x and x plus h, and so therefore it has to approach x. And so in the limit as h goes to 0, by continuity of f, we have to get f of x. In other words, as h goes to 0, c sub h goes to x, and f of c sub h therefore goes to f of x. And so that's the result. The derivative of this function, integral from a to x of f of t dt from a to x, its derivative with respect to x is simply equal to f of x. So I can write d by dx of this is simply f of x. Well, the fundamental theorem of calculus then, in its second part, says that if I want to calculate the definite integral of a continuous function, and if I can find an antiderivative for that continuous function, which is valid on the entire interval of integration, then I simply evaluate that antiderivative between the endpoints of integration. We have a useful notation for this, which basically breaks the process up into two steps. We first find a function whose derivative is the integrand, and then second, we do the evaluations. Let's look at this. So a useful notation is for any function, capital F of x, when I write vertical line, a little a down near the bottom of the vertical line, a little b up near the top. What I mean is to evaluate capital F at the upper limit b and subtract what we get by evaluating at a. So that means when f prime equals little f, when capital F prime equals little f, that's to say capital F is an antiderivative of little f on the closed interval a, b, then by the fundamental theorem of calculus, the definite integral from a to b of f of x dx is capital F of b minus capital F of a, which we write to begin as capital F of x evaluated between limits a and b with this vertical line notation. So you see what this does is it'll make the calculation run smoothly. We first look at the integrand, try and think of an antiderivative as a function of x to put there, so when we look at it, for instance, we can check it by differentiating with respect to x and see that we get the integrand. So once we're sure we have an antiderivative, we put the vertical lines from a to b, and then looking at the function and concentrating on these numbers, I can then put in the top number, f of b, calculate, and then minus, put in the bottom number, little a, for x, calculate f of a. So we take the difference of those two values, and we have the definite integral. Well, let's use the fundamental theorem of calculus to compute a definite integral. Here, I have the definite integral from 0 to 4 of the quantity 3x minus x cubed over 4 dx. So we begin by looking for an antiderivative of this integrand. What's a function whose derivative is 3x? Well, obviously, if I take 3 times x squared, when I differentiate that, I will get the power lowered by 1 back to x to the 1 power. But notice by the power rule, a factor of 2 is going to come out front, so I get 2 times 3x if I differentiate this. So the strategy is then divide by 2. And so now when I differentiate with respect to x, I get 3x exactly. In other words, 3x squared differentiated gives 6x over 2, which is back to 3x. What about this second term, x cubed over 4? Well, if I differentiate the fourth power of x, x to the fourth, I get 4x cubed. And so how can I fix it so that I get x cubed over 4? Well, let's look. We have x to the fourth when differentiated is going to give 4x cubed. So let's divide by an extra factor of 4. Now, when I differentiate, the 4 comes out front, cancels one of the 4's, leave it, and our power gets lowered to x cubed. And we have then x cubed over 4. And so if I take the difference of these two expressions, the derivative of that whole expression now will give me 3x minus x cubed over 4. So I have in fact found an antiderivative of this integrand. And so now by our fundamental theorem of calculus, I know that if I take this antiderivative and evaluate between these two limits, I get the value of the definite integral. So we begin by putting in x equal 4. 3 times 4 squared divided by 2 minus 4 to the 4th power. Down here in the denominator we have 4 squared. And then we subtract what we get by putting 0 in for x. Well, of course, that's just going to be 0. So, well, what do we have? 2 into one of the 4 factors leaves a 2. 2 times 3 is 6 times 4 is 24. Minus 4 to the 4th over 4 squared is 4 squared, so we have minus 16. And that leaves 8. So that means finally 8 is the definite integral from 0 to 4 of the quantity 3x minus x cubed over 4 dx. Let's use the fundamental theorem of calculus to evaluate a definite integral. Here I want to evaluate the definite integral from -1 to 1 of the quantity r plus 1 all squared. So what I begin by doing is asking myself, what can be an antiderivative of r plus 1 quantity squared? Well, generally speaking, differentiating lowers power, so I might start by looking at r plus 1 quantity cubed. If I differentiate this, I will get 3 times the quantity r plus 1 squared times the derivative of what's inside, which is 1. And so consequently, I would get 3 times r plus 1 squared. That's 3 times what I need. So let's just divide by 3 to make up for that. Now when I differentiate, the 3's will cancel, and I'll just end up with r plus 1 squared. So there's an antiderivative in the fundamental theorem of calculus. Says if I evaluate that antiderivative between the limits -1 and 1, then the result equals the definite integral I'm interested in. So now we have an easy job to do. We begin by taking the upper limit 1, substitute that for r. So 1 plus 1 is 2, and 2 cubed is 8. So we have 8/3 minus what we get by taking the lower limit and substituting in for r. Well, when I put r equal to -1, -1 plus 1 is 0, and so the whole value just collapses to 0. We have 8/3 minus 0, and so the result finally is 8/3 for the value of our definite integral. Well, we may not know how to anti-differentiate the absolute value function, but let's not let that stop us. Here, I want to find the definite integral from -4 to 4 of the absolute value of x dx. Now, I may not know how to anti-differentiate that, but one thing I know about the absolute value of x is that if x is positive, absolute value of x equals x, and if x is negative, absolute value of x equals the negative x. And I know how to differentiate x, I know how to anti-differentiate x, and I know how to anti-differentiate negative x pretty easily. So let's take this definite integral and use the fact that definite integrals can be broken up into pieces. We can integrate from -4 to 0 of absolute value of x dx, plus the integral from 0 to 4 of absolute value of x dx. Now, between -4 and 0, absolute value of x is simply negative x. So we get the integral from -4 to 0 of negative x dx. Plus, on the interval from 0 to 4, absolute value of x is simply x. Now, one thing I can do here is take the negative sign out of the integral. And when I do, I have the negative of the integral from -4 to 0. And so let's write that. Negative of the integral from -4 to 0 x dx plus the integral from 0 to 4 of x dx. So we have these two definite integrals to compute. Now the negative of the integral from -4 to 0 is the same as the integral from 0 to -4. We can reverse the direction of integration. So we have the integral from 0 to -4 of x dx plus the integral from 0 to 4 of x dx. By doing this, what I've turned the problem into is two integrals where the integrand is the same in each case, namely x. So let's ask ourselves, what is an antiderivative of x? Notice if I differentiate x squared, I get 2x. So consequently, if I take x squared and divide by 2, the derivative is just x. So here I have x squared over 2 for the first definite integral. We want to evaluate from 0 to -4, plus, for the second one, x squared over 2 evaluated from 0 to 4. Now notice what's going to happen. This function x squared doesn't care whether you put a -4 in or a +4. It gives you the same thing. So both of these quantities are the same. In effect, I have twice the quantity x squared over 2 evaluated from 0 to 4. So I can cancel those 2's, put the 4 in for x and square. I get 16. Let's see how we can use the definite integral to calculate the area between two curves. Let's start with the area between a graph of a function and the x-axis. Here I've shown a picture. Here's the graph of a function y equal f of x, and here are the vertical lines x equal a and x equal b. So if I want the area enclosed by these two vertical lines and trapped between the function's graph and the x-axis, notice it consists of several pieces. I've denoted these R1, R2, R3, and R4. So what we're interested in then is what is the total of those areas. So the area between the graph of the function and the x-axis here would be the area of R1 plus the area of R2 plus the area of R3 plus the area of R4. Now, each one of these is related to a definite integral. Where the function is above the x-axis, the area of the region is exactly equal to the definite integral. But remember, where the function goes below the x-axis, the definite integral gives you the negative of the area between the curve and the x-axis. So consequently, what I want to do is find these points where the graph crosses the x-axis. Say this is C1, this is C2, this is C3. What I do is then integrate the function from a to C1, then integrate the function from C1 to C2. That integral will be negative, and I'll just throw away the negative sign. That is, I'll take the absolute value of the definite integral of f from C1 to C2. Then I'll take the definite integral from C2 to C3. Of course, it'll be positive, but I could say, okay, take the absolute value of that definite integral, and then take the definite integral from C3 to B finally. We see here that would result in a negative number, but I take the absolute value, and that turns it into the area between the curve and the x-axis. And so adding those areas up, in effect, means adding up the absolute values of those definite integrals from the successive crossing points. That is, the absolute value of the definite integral from a to C1 plus the absolute value of the definite integral from C1 to C2 plus the absolute value of the definite integral from C2 to C3 plus the absolute value of the definite integral from C3 to B. Another way to think of this is, if I were to take the absolute value of the function f, it would flip these parts where the curve goes below the axis up above the axis. In that case, the absolute value of f follows that curve, and notice the area under absolute value of f gives exactly what we're talking about. So when we're doing this, what we're really doing is taking the definite integral of the absolute value of f. Now, in general, if I wanted to do a similar thing for the area trapped between two curves from x equal a to x equal b, I'd be dealing with something like f of x equals the absolute value of h of x minus g of x, where h and g are two functions. If I took that particular choice of f of x, it would always be greater than or equal to 0, and integrating the absolute value of the difference would give me the area between the curves. In any case, that would be the same problem as actually finding the area trapped between the difference h minus g of x and the x-axis. So any way you think of it, basically what you're doing is finding the crossing points. If I'm dealing with two different functions, I merely want to find the successive crossing points, take the definite integrals of the differences there over the given intervals, and take their absolute values of those resulting definite integrals and add them all up. Well, let's summarize this procedure then. To find the area between the graph of y equal f of x and the x-axis over the interval ab, one subdivide a comma b at the zeros of f. Now, it's important here that you find every zero of f. If you miss one, then you will be getting part of the integral where it goes below the axis, canceling part of the positive part, and the value will come out too small. Second, integrate f over each subinterval. 3, add the absolute values of the integrals. Again, then, what we're in effect doing here is calculating the definite integral from a to b of the absolute value of f of x dx. Let's see how our procedure for finding the area between a graph and the x-axis works in practice. Find the area between the x-axis and the graph of y equal x cubed minus 3x squared plus 2x for 0 less than or equal to x less than or equal to 2. So what we have to do to begin with is find every point in this interval at which this graph crosses the x-axis. That is, we want to set it equal to 0 and solve. Well, to solve a polynomial equation, it's best to factor, and you can see right off we have an easy factor of x that comes out. So y is x times the quantity x squared minus 3x plus 2. Now when I look at that quadratic expression, it's easy to factor. It's simply x times x minus 1 times x minus 2. Let's multiply it out to check. X times x gives the x squared, negative x and negative 2x gives the negative 3x, and negative 1 times negative 2 is plus 2. So there we have it. And by having it completely factored, now I know exactly where this graph crosses the x-axis. It crosses at x equals 0, at x equal 1, and x equal 2, and that's it. That's every crossing. So consequently, we have x equals 0, x equals 1, and x equals 2. So between 0 and 2, the area trapped will be the absolute value of the definite integral from 0 to 1. I'll just abbreviate the integrand as y dx, plus the absolute value of the definite integral from 1 to 2 of y dx. Well, we don't anti-differentiate products very easily, so the whole exercise of factoring there is not going to help us find the antiderivative. we have to go back to the original expression. That is, we have to look here at x cubed minus 3x squared plus 2x, because we can easily get antiderivatives for each term. The antiderivative of x cubed, well, that would be x to the fourth divided by 4. The antiderivative of 3x squared, well, we spot that right away as the derivative of x cubed. And the derivative of 2x we spot is the 2x itself is the derivative of x squared. So consequently, the antiderivative of x cubed, x to the fourth over 4, minus x cubed, which is the antiderivative of 3x squared, plus x squared, which is the antiderivative of 2x, will be an antiderivative for y. So now what we need to do, you see, is take this antiderivative, evaluate between limits 0 and 1, evaluate limits between 1 to 2, and take the absolute values of those results. Now that would look like this. In other words, the definite integral from 0 to 1 of y dx is x to the fourth over 4 minus x cubed plus x squared, evaluated between limits 0 and 1, and then take the absolute value of the result. The definite integral from 1 to 2 of y dx in absolute value is the absolute value of x to the fourth over 4 minus x cubed plus x squared, evaluated between limits 1 and 2, and take the absolute value. So because we're dealing with this same antiderivative in each case, the best thing to do, in fact, notice the one evaluation is going to occur in both problems there, just make a table. Here the points we're having to evaluate are x equals 0, 1, and 2. The antiderivative of x to the fourth over 4 minus x cubed plus x squared, that's our antiderivative of y. And so we evaluated each of these points. At x equals 0, it's obviously 0. We can easily see that at x equal 1, it gives a fourth. After all, 1 minus 1 is 0, and 1 over 4 gives a fourth. And when I evaluate at x equal 2, we get 0. That is, 2 to the fourth is 16 over 4 is 4. Minus 2 cubed is 8, so 4 minus 8 is negative 4, but then 2 squared is plus 4, and the negative 4 and 4's cancel out. So our curve is actually crossing the x-axis at the endpoints of our interval that we're interested in. And so the definite integral from 0 to 1 is 1/4 minus 0, and so its absolute value is clearly 1/4. The definite integral from 1 to 2, well, that will be the 0 minus a fourth. So there we get negative a fourth. But remember, we want to take the absolute values of these definite integrals. So we end up with 1/4 and 1/4. We add those results, we get 1/2. And so there we easily see, using a little table, that we can efficiently do these evaluations that are required to compute the area between the function and the x-axis. Well, we've seen how the fundamental theorem of calculus is a result of the mean value theorem for definite integrals, and how we can use it to efficiently calculate definite integrals when we can anti-differentiate, especially when you're trying to find the area between a function and the x-axis. Remember, you must find every crossing point. If you miss a single one, it'll ruin your calculation. So be careful, and now that you've seen these problems, try some on your own.